Now that we've developed the material derivative, let's introduce the theorem of the transport theorem. The theorem 1 in equation 124 will let capital omega t denote an arbitrary volume that is moving with the particular fluid, and let f of xt be a scalar or vector function dependent on position and time within the fluid. The transport theorem then states that the ordinary derivative of the volumetric integral of f is equal to the volumetric integral of partial f partial t plus u nabla f plus f divergence of u. We can write 124 as 125 as d dt f, which is a volume integral. The left-hand side remains the same. And the right-hand side we can break apart as a volumetric integral of partial f partial t plus a surface flux integral, Ādros-Grotjie's theorem, of fu dot n, where n is the surface normal. So here's a surface integral of these two terms. Now, let's prove this theorem. Consider the transform of x mapping omega 0 to omega t. So this is how the fluid partial deforms. And x goes as x of cap xt, as we discussed in the previous video. Then we can write 125 as the volumetric integral of f goes as the volumetric integral of f with the Jacobian at time 0 to capital F of Jacobian with, of course, cap x at time 0. We can then show from 125, 126 that the left-hand side is the same, and it'll be equal to the integral at time 0 of d dt fj plus f d dt j. We can now write the larger equation, integral at time 0 of d dt fj, which is volumetric integral at time t of partial f partial t plus u dot nabla f, which you should see as a material derivative. All that would remain is to prove the Euler formula, which has been done previously. If the fluid is incompressible, then of course the volume that fluid parcel encompasses any particular volume from any time to any other time in either direction will be conserved. This is the true definition of incompressibility of fluid. Note that the transport theorem we can start using and writing it as 131. And if we set f to be unity, we can write d dt of the volume will go as d dt of the volume of unity and replace in j for omega 0. Based on the particular Euler formula, and given that we've previously shown that the Jacobian is between 0 and infinity, positive, scalar, and the fact that the choice of the domain omega t via omega 0, if it's incompressible, is necessary and sufficient for the fluid to be compressible. And we can recover D'Alembert's condition that the divergence of u is 0, indicating that the fluid is incompressible. If we let rho be the density or mass per unit volume of the fluid at any point x in time t, then the mass of the finite volume omega could be written this way, that if we integrate the volume of the density dx, we can recover the mass m. This particular conservation of mass will state that the mass of a fluid of material volume omega does not change as omega moves through the fluid. And we can write 135. The ordinary derivative of the volumetric integral of rho of xt will be 0 if the fluid's incompressible. Using equation 125, we can then write the volumetric integral at any time t, partial rho partial t, plus the divergence of rho u dx is 0. And this is, of course, the compressible form. And we recover the beautiful equation 137, which is partial rho partial t, plus the divergence of rho u is 0, which is the first of the Navier-Stokes equations. The particular principle of conservation of mass can also be expressed this way. Let omega be a fixed volume. Then we can write the ordinary derivative of the density within a fluid parcel will go as the negative of the particular surface fluxes, negative of the surface flux integral of rho u dotted with the normal surface vector. This is a particular rate of change of mass in a fixed volume omega and will be equal to the mass flux through its particular surface. And we can write this nice general formula in integral form.